So to move further and to solve Einstein equations, let us make the following change of coordinates. Let us change dt to a of eta d eta. Then our metric that we are discussing will acquire this form, d eta squared minus dr squared 1 minus k r squared minus r squared d omega squared. So, and we have that the metric has this conformal factor and is conformal to this metric. This eta is called conformal time. Unlike this t, this eta is conformal time. We actually have encountered this eta in the lecture on Oppenheimer-Snyder collapse. That is exactly that eta which we have seen there. So then, from the equation 3a dot squared plus k equal to 8 pi kappa rho a squared, which is 0 component of Einstein equations, we obtain the following relation. We obtain that dt is equal to plus minus, because we have to extract square root, times dA square root of 8 pi kappa over 3 a squared rho minus k. So we have to find rho through a, plug it here, and then integrate, so to say. And plus and minus corresponds to the solutions that are related to each other by time reversal. Now, using this relation and this relation, we find that eta is plus minus dA over a square root of 8 pi kappa over 3 a squared rho minus k. And this is, now we're going to find from here a of eta, and then from here t of eta. So our goal is to find a of eta and then t of eta from these two equations, and to use here the relation between rho and a for 6 different situations. For k equal to minus 1, 0, 1, and omega equal to 0 or 1/3. So for 2 types of equations of state and 3 types of spatial sections. So let us start with the case of k equal to 1 and omega equal to 0. This is the case actually we have encountered in the lecture on Oppenheimer-Snyder collapse. Then, from the fact that rho times a cube is constant, this is the case as we remember for this situation, we denote this constant as m over 2 pi squared. We use here a bit different notation from the lecture in Oppenheimer-Snyder collapse. So to say this m is the total mass of the universe, because this is related to the total mass, and it, so to say, remains constant through the evolution. So if we plug this into here, and take the integral, we obtain, in this case, that a of eta is equal to 2 kappa m divided by 3 pi 1 minus cosine of eta. And from this relation, we can find that t of eta, of course, we have fixed the integration constant here and here to fix this. That sets up the initial conditions. 3 kappa m over 2 kappa m over 3 pi times eta minus sine eta. So one can see this is a solution we already encountered in case of Oppenheimer-Schneider collapse. And then the physical meaning of eta is now obvious, etc., etc. So now for small eta, this solution describes the following situation. For small t and small eta, so when we start the evolution of the universe, A of t, as follows from here, is proportional to t to the power 2 over 3. Then, so our evolution starts at eta equals to 0, when A is equal to 0, A equal to 0. Then as eta goes by, as eta equals to pi, and hence t equals to 2 kappa m over 3, the universe reaches its maximal size equal to 4 kappa m divided over 3 pi, and then shrinks back. So we have the following situation, that the scale of the universe expands from 0 and then shrinks back. So this is eta equal to 0, eta equal to pi, eta equal to 2 pi. So, and this is A. That's the situation we encounter for this case. So the universe expands and then shrinks back. This is what we encounter in this case. So we continue our study of the metric ds squared A of eta squared times d eta squared minus dr squared 1 minus kr squared minus r squared d omega squared, where dt is equal to A of eta d eta. This is a relation between conformal time and regular time. And dt is equal to, and we restrict our consideration to the case of plus sign here, dA square root of 8 pi kappa over 3 a squared rho minus k, and also hence to the plus sign for the eta dA over a square root of 8 pi k kappa over 3 a squared rho minus k. So we have already considered the case when k equal to 1 and omega, the relation between rho and p, is equal to 0. In that case, all sections, so we continue now our consideration with the case of k equal to 1 and omega equal to 1/3. This case, again, one more clarification to the previous situation and to this one. For this case, I remind you that every spatial section in this metric is a sphere, three sphere. And we have encountered the situation that the size of this 3 sphere starts its expansion from 0 radius, gets to some final value, and then shrinks back. In this case, we again will encounter this situation with a little bit different behavior of the radius. So because in this case, unlike the previous situation, in this case we have rho equal to A4, which is multiplied by A4, which is equal to constant, rather than A cube. Let us denote this constant as 3A1 squared over 8 pi kappa. And this is constant. This is a convenience, for convenience reasons. If we plug this constant into here, then we immediately obtain that A of eta is A1 sine eta, and T of eta is equal to A1 1 minus cosine of eta. So as we start at eta equal to 0, T equal to 0, A is 0. So we, again, start, the universe starts its expansion with 0 size, expands to a finite size as eta goes by, at eta equal to pi over 2, it gets finite size, and then shrinks back to 0 size. All this consideration corresponds to plus sign. Minus sign would correspond to the time reversion of this solution. The same is true for the case of k equal to 1 and omega equal to 0. So, and let me say one more thing, that for small t, when t is of order of 0, for the very beginning of the expansion, it's not hard to see that a of t is proportional to the square root of t. And rho is proportional to 1 over t squared, as follow from the formulas. Let us continue with the case of hyperbolic spatial sections. In this case, k equal to -1, and we start our consideration with omega equal to 0. So dust in the case of, so in this case, every spatial section is a hyperboloid. And for this case, we encounter that r times a cube is constant. Let us denote this as 3a0 over 4 pi kappa. Well, this is just a notation. This is constant. The reason for the notation, well, for example, the reason for this notation is just because a1 appears as the amplitude here. And the same we will encounter here. If we use here this and plug it here, we obtain that a of eta is equal to hyperbolic sine, or a0, this is a0, times hyperbolic sine, cosine of eta minus 1, and t of eta is a0 times hyperbolic sine of eta minus eta. Well, once we have got this, from this equation we can find t of eta. Now we encounter the following situation, that the universe starts its expansion from 0 size and continues it eternally. It doesn't shrink back, unlike this situation of the closed universe. And again, at the it starts its homogeneous expansion from 0 size at t equals to 0. And at the beginning of the expansion, when t is very small, a is proportional to the t 2/3. 2/3. In fact, it's actually similar to the case of k equal to 1 and omega equal to 0. The expansion also starts with such a behavior. And we're going to continue with other cases now. So we continue our discussion of this space-time for several different situations. We already discussed the case of k equal to 1 and both omega equal to 0 and omega equal to 1/3. And we already discussed the case of k equal to -1 and omega equal to 0. We continue our discussion with the case of k equal to -1 and omega equal to 1/3. In this case, we encounter that rho times a4 is constant. We define this constant to be 3a1 squared over 8 pi kappa equal to constant. And then we obtain, plugging this into here and then into here, we obtain that a of eta is a1 hyperbolic sine of eta, and t of eta is a1 times hyperbolic cosine of eta 1 minus 1. Again, we encounter the eternal expansion of open universe. Open because for this case, spatial sections are hyperboloids, not spheres. They are open. So eternal expansion, and it starts also with 0a, at eta equal to 0. We have a equal to 0, t equal also to 0. And actually at the beginning of the expansion, when t is very small, A of t is proportional to the square root of t. You see at the beginning of the expansion, in every case for the radiation and for the dust, we encounter the same kind of behavior. I mean, for the dust, the same independently of the type, and for the radiation, the same independently of the type. But they are different. For the dust, differs from the radiation. Now, for the case when k equal to 0 and omega equal to 0, one can directly integrate this. As one can see. And in this case, well, first of all, we encounter rho a cube equal to constant. And then, as a result, from the integration from here, we encounter that A of t is equal to constant times t 2/3. And the behavior, so for this case, this is always like that, this relation. For the other cases, such a behavior for the dust is only at the beginning of the expansion. And finally, when k equal to 0 and omega equal to 1/3, we, as usual, have rho a to the 4th is constant. And directly, using this directly here in this equation, we obtain that A of t is some constant times square root of t. Again, always we have this relation for this case, while for the radiation, for the case of k equal to 1 and k equal -1, such a relation is valid only at the beginning of the expansion. Now let me say a few words that at present our universe with a good precision corresponds to the case k equal to 0 and omega equal to 0, up to one important issue that recently well, several comments are in order. First of all, at the beginning of the expansion of the universe, we expect that the predictions say that there was an era when this was valid, and moreover, there was an exponential inflationary expansion. There are signs saying that. And also now we see that the situation is not quite adequate, because there is a non-zero cosmological constant, so-called dark energy, which describes exponential expansion. Again, in all this lecture, we have assumed that lambda, cosmological constant, is 0, while inflationary expansion corresponds to the case when lambda is not equal to 0, and that this situation will be described in the next lecture, not in this one. So this inflationary expansion is important to describe our present universe. Apparently, observational data show that lambda is not 0, but very small. And also, there are some signs that at the beginning of the universe, at early stages, lambda was big and not 0. That is original inflationary expansion. And that will be discussed in the next lecture.